Welcome to Pre-Calculus. Today we will investigate power pendulum scenarios, focusing on finding the period of a pendulum given a pendulum length, as well as finding a pendulum length given a specific period. Let's take a look at two examples. Let's head over to our note screen. Our example here is about the Acme rocket. So the Acme rocket ride at Six Flags had a pendulum that was a height of 84 feet. Once the pendulum was released from its raised position, how long would it take for the ride to swing back and forth once? So perhaps you've taken a ride on the Rockin' Rocket. It's not at Six Flags anymore, but it was a classic instance of a pendulum. Let's just investigate what is a pendulum before we look at the problem more closely. So a pendulum is an object that is attached to a fixed point. And the motion of a pendulum really is swinging back and forth. So one famous pendulum is this Rockin' Rocket. There's also other different types of pendulums. Grandfather clocks have pendulums built into them in order to make the clock move. Well, it swings back and forth. So it does require some kind of initial pull to the side, and then it's released. And as it's released, the object swings back and forth pretty much without losing a lot of its motion. It swings back and forth, back and forth, back and forth. Now we define two measurements on a pendulum. The first measurement that we define is the length of the pendulum. And that's from the fixed point down to the object. And usually that's a string or some kind of rigid stick. But that is one of the basic measurements of a pendulum is the height. The other basic measurement of a pendulum is what we call period. And let's define period because we're going to have to calculate that here in one of our examples. So the period is the time it takes for the pendulum to swing back. Let me catch up to my words. For the pendulum to swing back and forth once. The period is the time it takes for the pendulum to swing back and forth once. Now, let's define that here on our picture. So if I have the pendulum pulled over to the left side here, let's say that it's at that far extreme left, the period would be the time it takes for it to swing to the right and then back to the original position. So keep in mind, the period is that time really kind of for a double swing. It goes one direction and comes back, and that would define our period. Well, let's take a look at this question about the Acme rocket. So we're going to give ourselves a formula, and really before that, let's just sketch it again so we got the measurements here on our specific example. So here is the Acme rocket. So that was a ship that was attached to the end of a pendulum. And the claim here is that that was 84 feet long. And our question is, what's the amount of time that it would take for the Acme rocket to swing to the right and back to the left? What's the time? Now, we've got a formula that governs this motion of a pendulum. So let's record that formula. And it is the period, which we're going to call capital T. So we do that because it's really about time, equals 2 pi times the square root of a fraction. So it's the length of the pendulum or the height divided by g. Now, G is something that is a constant on our planet, and what we call it is the gravitational constant due to gravity. Kind of in the name, gravitational constant. And let's give it a value. It equals, G equals 9.8 meters squared. I'm sorry, meters over second squared, which in terms of feet is 32 feet per second squared. So definitely you'll want to choose the one that matches your measurement. So for us, if we're in feet, the height of the pendulum is 84 feet, we're going to select 32 feet per second squared. Now, that said, all we have to do is put in two of these values. Really, we need to put in the length of the pendulum and the value for G, and then we can solve using this formula. So let's do that. So I'm going to put in 2 pi. And as I'm recording these values, I want to ask, why are we having this 2 pi as part of this formula? Why 2 pi? So the length of the pendulum is 84 feet. And G for feet is 32 feet per second squared. So we'll calculate this, but first things first, why do we have 2 pi as part of this formula? Well, remember from geometry that the circumference for a circle is 2 pi times the radius. Really, a pendulum is moving in kind of a piece of a circle. In fact, if you ever rode the Rock and Rocket, you know that it doesn't just travel in an arc in that traditional back and forth pendulum movement. It actually went upside down. It was a true thrill ride. But that's where the 2 pi is coming from. It's part of the shape of the motion of a pendulum is circular. Well, let's go over to Desmos to get a simplified answer there. So what we've got there, 2 pi squared of 84 over 32, that's exact. Let's see if we can get a decimal approximation. So we'll head over to Desmos. And let's type that in as we found it. So I'm just going to put the fraction. Before I do so, let me type in 2 pi. So 2. And then on Desmos, you can just literally type pi and it'll convert it to the value. Let's choose, I may have to highlight this to get the square root over it. Go to the keypad and then select square root. And I'll have to type it in. So lesson learned, put your square root first. The height of it is 84. And the acceleration due to gravity in feet is 32. And that gives us this approximate value of 10.18 seconds. 10.18 seconds. Let's head back and finalize our answer there. So that, again, for our pendulum, for the Rock and Rocket, 10.18 seconds. And we'll box that. Again, I put the wavy sign to indicate that that's an approximated answer. Okay, so let's take a look at our second question here. So it's the same setup in terms of the object. It's the Acme rocket pendulum again. The question is, how long would it take, or how long would it need to be? What should its height be for it to take 30 seconds to swing back and forth once? So it's the same scenario. What I need to look at is the equation to say, can I use that equation in the form we used it the first question? So t equals 2 pi times the square root of the length or the height over g. So what we're looking for is really this length if I know time to be 30 seconds. So it's not as convenient to just plug in our values because the one that we're looking for is in a way buried in a fraction in a square root. So there's two ways we can go about this. We can either put in our values into this form and then solve for the height, or we could solve for the height and come up with a new equation that would be for height. Let's do that second option because it'll be useful to you if you have multiple questions to be able to have an equation for height instead of for time. Well, let's rewrite this. In fact, I'm just going to erase these red marks and let's solve this for length. So I'm going to start by getting rid of this 2 pi, and what we'll do is we'll divide that right side by 2 pi. Now on this right side, that's going to cancel, and it's going to show up there on the left. So then our next step will be t over 2 pi equals the square root of length over g. Now the question is, how do I cancel that square root? Remember, the inverse operation to square root is the squaring. So if I square that right-hand side, the square and the square root are going to cancel each other out. They're inverses. And then just to keep the balance on the equation, I'll put parentheses and square that fraction time over 2 pi. Now let's see what we've got. So at this point, we've got parentheses time over 2 pi, close parentheses to the power of 2, equals the fraction length over gravitational constant. So only one last thing to solve away. So I need to get just length by itself. So I've got g down here in the denominator. So I can multiply by g. That'll cancel. And make sure I put the square, I forgot that, in the first recording. And that really gives us our new equation. So I'm going to bump this up because I've run out of room. Plus, we'll need it at the top of the screen to solve. So this is now, and I'm going to flip it around, length equals g times parentheses time over 2 pi, close parentheses, squared. And that is a much more convenient equation to solve for the length if I'm given the time. Well, let's use it. So we created it, let's use it. So really I'm interested in the time of 30 seconds. So again, I'm going to put in for g, since we're dealing with feet, 32 feet per second squared. And remember, that's just the constant value that we always take for the gravitation due to the acceleration due to gravity. So 2 pi is part of the formula. I'll just put it there. And then the time we're interested in is, from the question, 30 seconds. And I keep forgetting that this is squared, which is dangerous. But we fixed it. So like we saw before, the answer that we just wrote is exact. I haven't got a lot of simplification done to it, but whatever it is, it's exactly the value. But let's get an approximate value. So again, I'll put the wavy signs using the calculator. So I'm going to head over there. Let's share the Desmos view. And like we did, I'm just going to type in what I had input there in that modified equation. So 32 I'm in feet, times parentheses, and then there we're going to put our time over our 2 pi. So again, we were interested in 30 seconds divided by 2 pi. And again, for pi, you can just type pi. It'll translate it as 3.14. And then that I have to square. And that gives us this value of 729.51 feet. So an enormously lengthy pendulum, for it to take 30 seconds for it to swing back and forth 1 time. Well, let's head back to our notes to finalize that answer, and then just make a brief observation. So 729.51 feet. So a good question to ask is how that compares to our first values. So here, for a period of 30 seconds, our pendulum had to be over 700 feet long. So in our first example, it was about 10 seconds for 84 feet. So the time increased by about 3-fold. If I multiply 10 by 3, I get 30. The question is 84 times 3 729? Did the length increase by 3? So again, let's catch that. It's 84 times 3. What do you think? Let's multiply it out. So that's 2, carry the 1. It's not. So the question really is, why isn't it just tripled? If I triple the time, why isn't the length of the pendulum simply tripled? What do you think? Excellent. We are squaring stuff. So keep in mind, anytime you square things, the rate of increase is much higher than if you simply had it to the first power or left it linear. So what we're seeing is that this definitely 729, it's much higher than 3-fold. In fact, if I multiplied by another 3, which would be equivalent to squaring 3, let's see what we get. So that becomes a 6, a 5, 756. So roughly in the ballpark of our 729, if I square that 3 before I consider how many times the length needs to be. Okay, so some insight into some relationships between a square root function and a square function. So thank you for joining for this applications of power pendulum scenarios. I'll give you a chance to go work on some of your own problems. Thank you for joining. See you next time.